All right. So again, thank you, everyone. My name is Liz Marai. I'm the Director of Graduate Admissions for 2022-2023 at University of Illinois, Chicago, Department of Computer Science. I am also a professor of computer science. UIC opened in 1965 as University of Illinois Circle, and it started being called University of Illinois, Chicago, actually in 1982. It grew as a sister campus to the University of Illinois at Urbana-Champaign. So you can see we are a relatively new campus, but we, the College of Engineering and the Department of Computer Science in particular, are a rising star with the highest growth rate in the United States and more than $10 million in terms of research funding per year. In terms of where we are located in the United States, well, this is the Great Lakes region in the United States, and we are right here at the south tip of Lake Michigan. And this is a picture of downtown Chicago, and our campus is where the yellow arrow is. Chicago is a wonderful, very attractive metropolis. We have 4 seasons. We have snow in the winter, but we also have beautiful fall and spring and beaches in the summer. We have a lot of large international communities, a vibrant cultural life, and excellent public transportation. And we're also not as expensive as the East Coast or the West Coast. The American graduate educational system continues to be one of the best in the world. International students, in fact, represent the majority of graduate students at UIC. Our department has more than 40 tenure-track faculty members working mostly in innovative areas such as networking, mobile computing, security, electronic visualization, NLP, and so on. In terms of our graduate program, it is one of the best graduate programs in the US and the world, and it offers unique opportunities for professional development. On the right-hand side, you can see example of companies that hire from the UIC College of Engineering. UIC is also a place of discovery. UIC is the birthplace, for example, of the shingles vaccine, major drug discoveries, and so on. Special effects for the Star Wars series, artificial leaves developed at UIC that help fight climate change, and so on. The other thing to know about studying in the US and at UIC is that most Americans are immigrants, and so they have respect for other immigrants. And in general, they tend to think that a foreign accent is cute. It's not a sign of an inferior class. Our department in particular has a special program for underrepresented groups and a lot of support for international students and also a lot of computer science communities. Our department is also the only computer science department selected by Capital Ventures, a philanthropic company financed by Melinda Gates, to implement a $6 million pilot program to diversify computing with particular emphasis on women and other underrepresented groups. In terms of our graduate program, we have a master's program, for which students typically pay for tuition and so on. That's about $30,000 per year. So it's expensive. It's not as expensive as other graduate programs in the United States. But the reason we're here is to talk primarily about our doctoral program. For our doctoral program, students are hired during their studies, so you do not pay to study. You get hired either as a teaching assistant or a research assistant. A small number of students receive university fellowships or other types of fellowships as well. The doctoral program comes with a stipend of around $2,000 per month, which is enough for a reasonable standard of living in the United States and for international travel. And it includes health insurance. Our students are funded for the duration of their studies, which tends to be 5 or so years. And again, they're funded via assistantships. So you work on research or helping with a teaching program and so on. There are also summer opportunities for students who are interested in the form of internships or appointments at the university in research labs. To be admitted to the doctoral program, it is not necessary to have a master's degree. It is also not necessary to have a perfect 10 on a scale of 10 grade average. It is also not necessary to have been an Olympian in the Olympics for mathematics or informatics and so on. It is also not necessary to have studied special areas typically not taught at the undergraduate level, for example, computational biology, security, data visualization, or robotics. And it's also not necessary to have prior publications, although they do help with the application process. What is necessary is to have intellectual curiosity as a sign of having research aptitude, to have the capacity to learn, typically shown by a grade average above 8 on a scale of 10, respectively 3.2 on a scale of 4, and to be able to communicate in English. In terms of what is necessary in order to apply, students need to take the GRE test, which is a test that checks your level of intellectual knowledge at roughly the level of high school or first years of college. We also require a test called TOEFL, or an equivalent English proficiency test. TOEFL is accepted by all universities. You need to have your school transcripts, a CV in English, 3 recommendation letters in English, preferably from professors who do some research, and a statement of purpose written in English. In terms of the costs, there's the application fee with fee waivers applied. There's the cost of the GRE test. The GRE test is $205, but it works for 5 schools. And then above the 5 schools, it's $27 per application, so it's not a huge deal. TOEFL, same thing as the GRE, and then sending the GRE score, sending the TOEFL scores beyond the 5 schools. Our department and college were very fortunate to be able to secure a fee waiver deal for the fall 2023 application cycle. Under this agreement, domestic students will pay $0 to apply to UIC, the College of Engineering, so the Department of Computer Science. International students still have to pay $100 for the international evaluation fee. In order to qualify for these fee waivers, the applications must be fully completed by December 15, 2022. And the fee waivers will be automatically applied to all the graduate applications coming to the Department of Computer Science. I want you to know that our faculty are very serious about admitting students they are interested in, and that the first stipend, if you become a doctoral student, will more than make up for the GRE, TOEFL, or application fees. In terms of preparing for the application process, we recommend that applicants check out the typical admission requirements thresholds first. For the GPA, for example, we expect at least 3.5 on a scale of 4 for the final 2 years of undergraduate study, as well as for any graduate work completed, and at least 3.2 out of 4 for all years of undergraduate study. The GRE average score requirements are a minimum of combined 300 GRE verbal and GRE quantitative score. Typically, we see at least 140 points on the verbal score and at least 150 points on the GRE quantitative score. We recommend that applicants take the GREs and the TOEFL to figure out whether they meet the admission criteria. We also recommend that applicants start early the application process and apply online using our graduate admissions website. We also recommend that everybody browses the research areas at UICCS and try to locate areas that appeal to them. It's worth noting that AI or machine learning applications make up almost 80% of the applications received at all departments ranked in the top 50 computer science departments, including UIC, which means that competition for artificial intelligence slots is very, very tough. Newer areas which are typically not offered in college are typically interesting and have more opportunities. So try to keep an open mind. Things like data science, data visualization, security, computer vision, programming languages. In terms of the application process, it's really important to find a faculty match. Around November or so this month, we recommend that applicants contact directly professors in their matching areas and ask for an interview. Don't be shy. It's important that the faculty know who you are by the time they review your application. It's also important that you list their names in the personal statement so we can route your application to those faculty members. And again, it's important to fully complete the doctoral application by December 15, 2022, in order to qualify for the fee waiver. And in terms of when would it be a good time to apply? Well, most of our applicants apply in their last year of undergraduate study. So their fourth year, also known as the senior year in the United States. In terms of what we're going to do today, first we started with an overview of applications for fall 2023. We're going to go into a set of brief research presentations from faculty for about 1 hour. And then we'll close with a questions and answers panel for about 15 minutes. You are welcome to ask questions using the Q&A mark on the bottom of your screen. And without further ado, let's move on to the most interesting part of today's presentation and talk about research areas at UIC. And again, today our goal is to expose listeners to the areas they might not have worked in during their undergraduate and so on. All right, share screen. I'm going to go first. So hello again. I'm Liz Marai. I'm a professor of computer science and a faculty member of the Electronic Visualization Laboratory, which was founded in 1973 by Tom DeFanti and Dan Sandin, and has been at the forefront of collaborative tech research since 1992. That year, EVL introduced the first projection-based virtual reality system in the world, named a cave. Since then, the lab has developed a wide range of collaborative technologies for data analysis, including the Cave and Sage, which is a type of collaborative software. On the top left, you can see a model of a Death Star, which was created in 1977 at EVL for George Lucas, including the computer graphics shown on the pilot's screen. We still have the plaster models for the Death Star in our kitchen. Our research is in human-centered computing. Here you see us helping NASA specialists model data for a mission to Jupiter's moon Europa, respectively working with psychiatrists to map the neural connections in a depressed brain. Specifically, we work in visual computing, which is computing with information in visual form. Our field lies at the intersection between data science, in particular the one built on statistical learning, computer graphics, and human-computer interaction. Our main conferences are IEEE Viz, Euroviz, Pacific Viz, Supercomputing, and so on. And our main journals are IEEE TVCG, CGA, CGF, but also domain-specific journals such as bioinformatics, biomed journals, and so on. Most of my group's work is interdisciplinary and collaborative in computer science, communication, biomedical, astrophysics, engineering, and so on. So we have a broad spectrum and we don't get a chance to get bored ever. As you can see, we are often problem-oriented, but we are also theoreticians in our field in studying how humans relate to visual data. For example, we learned that computational fluid dynamics experts tend to start analyzing data by defining and analyzing the features of interest. Here's an example. Think of an aircraft flying over us, leaving behind these white line-shaped trails. Have you ever wondered what these trails are? Why they are sometimes present and other times not? How and why do they form? Well, these trails are known as contrails. Essentially, aircraft engines emit ash particles, and under the right atmospheric conditions, these ash particles become encased in ice and they become visible. Like regular clouds, contrails provide shade, but they also trap heat radiating from the Earth's surface, and so they make global warming worse. Computational fluid dynamics experts, like our collaborators, analyze contrail formation using high-performance computing aircraft engine simulation models. Together with these domain experts, we built an interface to help them analyze contrail features, in particular, the shape of these contrails across many different simulations with different parameters. And in turn, this helps them design better, more efficient engines and experiment with different biofuels and so on. In general, we work with data with structure because that's one of the types of data that humans really need to see with their eyes, whether it's astronomy data or computational biology data. Another class of projects we work on relate to explainable AI in medicine, or XAI. Essentially, in the future, when a patient shows up at the clinic, the doctor will be able to collect data, then go into the cloud and retrieve a cohort of similar patients. And based on that cohort data, they will prescribe the treatment that will work best for their patient. So it's about big data from cohorts that can enhance clinical decision-making and care delivery, but applied to the individual patient level. However, behind genetic similarity, many treatments and outcomes depend on the spatial location and the extent of the disease spread in the body. So it would be helpful to group together patients who have a similar disease pattern. And the computational problem here is obviously, how do we measure spatial similarity? And once we start creating new clustering methodology using spatial data and get useful results, how do we explain the spatial clustering to clinicians? Here's an example from radiation therapy and explaining the new methodology to doctors. Here's another example looking at oncology symptoms reported by patients, which this time we model using association neural mining, and again, trying to explain to clinicians which symptoms show up together and which are delayed. If you're interested in this type of work, all you need is research aptitude and interest in human-centered computing. We'll teach what you need. And EVL alumni work at a lot of interesting places, many as data scientists. We hope you'll join us, and best wishes for your applications. All right, our next presenter is going to be Will Mansky. And hopefully I can find his presentation. Hang on. There we go. Right, share screen. Let's go.
Hi, I'm William Mansky. I do research in programming languages and verification. I'm interested in coming up with mathematical models of how programming languages work, and especially their complicated features like concurrency and communication, and using those models to prove that programs always do what they're supposed to do. So how can we go about proving that programs always do what we want them to do? First, think about how we write programs in the first place. Ideally, we start with some idea of what we want the program to do. Then we write some code and we run some tests. More likely than not, our code isn't completely correct. So some tests pass, some of them fail. We adjust our code, run more tests, and eventually when it passes all of the tests that we can think of, then we figure that the program is correct. Now, how can we do this same process but get a formal mathematical guarantee that the program will actually always do what it's supposed to do, not just for the few test cases that we've tried? Well, first, we need our idea of what the program should do to be something that's written formally in a mathematical language. Usually for this, we use formal logic, and we call this the program's specification. And in order to relate that to what the program actually does, we need a model of how the programming language works, also written in the same language of logic. This is what we call semantics, a formal description of what every operation in the programming language does and its effects on the values of things like memory, variables, the state of the program, the next instruction to be executed, and so on. And if these two things are described in the same logical language, then we can write a mathematical proof that every behavior of the program allowed by the semantics will meet the specification that we wrote down. And since we're computer scientists, we are not going to write this proof by hand. We're going to use software to do it. So the bulk of my work uses machine-assisted theorem-proving software to build proofs of correctness for programs. And the places where this gets interesting is when we have to specify complicated features of the program, like its effects on memory and I/O behavior, when we have to deal with weird corner cases and complicated details of the programming language's semantics, like programs that might have undefined behavior, or use concurrency or otherwise communicate, and where programs are complicated enough that they're likely to have bugs unless we build proofs that they absolutely work correctly. If we can put all of these pieces together, the result we get are real programs written in real-world languages like C that we've proved are bug-free, both free of common errors like out-of-bounds array accesses, null pointer dereferences, race conditions, and so on. And even stronger than that, that they always actually meet their specifications, that they do the right things for all inputs. The kinds of projects that I have ongoing now, including modeling features of languages like network communication and high-performance concurrency, applying these tools to interesting programs like web servers and database data structures, and developing the tools that we need to prove correctness of the programs that we're interested in the real world. So developing extensions to verification systems so that we can apply them to, for instance, real C programs, and finding ways to integrate the verification process into the coding process so that ultimately it may be possible for every programmer to verify their program as they write it and use formal techniques to get more information about what their program does and what they want it to do as they code. So if any of that sounds interesting to you, I encourage you to send me an email and consider applying to UIC.
All right, our next speaker is Saurabh Media.
Hello, everyone. I am Saurabh Media. I am an assistant professor in the computer science department at UIC. And I'm going to talk about our group's research. Mainly, we look at problems that are at the intersection of machine learning and graphs. You might be more familiar with machine learning. So let me introduce graphs. I'm assuming almost everyone here is using social networks such as Facebook or LinkedIn. So it is easier to motivate graphs as they are also graphs. Graphs are a powerful tool that can model many complex systems such as social networks. We just gave an example of Facebook. Here, we are also seeing example of how one can model infrastructure, molecules, even images as graphs. So at this point, I'm assuming we are convinced that graphs are a powerful object. Our group mainly focuses on graphs and related problems to solve via machine learning. We aim to work on both fundamental and applied research. I have taken a few threads from our research and showing you here. I will show you also examples from each of these 4 categories. So the first category is to build new ML architectures. Why do you need it? In the last few decades, there were many sophisticated algorithms that have been built. We are revisiting them and trying to take our data and machine learning point of view and aiming to improve them. An example would be to compute graph similarity that has application in drug discovery as well as computer vision and many other domains. This is a complex problem as it is computationally hard. I mean NP hard. We are aiming to design machine learning based algorithms to exploit the data regarding the problem as well as previous algorithm structures to make better ones with machine learning. So while we are talking about machine learning, the question of interpretability comes naturally because we all want to build interpretable machine learning algorithms. We are also building similar structures. For instance, the figure is showing a formaldehyde where the red part is responsible for a particular property which is called mutagen, which prevents a molecule to be useful for drug. So we are building methods which can show that how we can change this bond in the next figure to remove this mutagen property. So we are also looking for building interpretable machine learning algorithms. So next thread is on application. We have already seen 2 fundamental aspects of our research. Here we are aiming to design better networks to improve infrastructures. We are seeing an example of Senegal and its map during flood with all the roads, and red roads are showing where floods happened. Now we are asking questions like, can we monitor certain roads or can we make new roads to prevent this kind of disruptions of not completing trips during this flood? So we are aiming to make better infrastructures for disaster response. One more application domain, what we are looking at is to improve social systems using machine learning as well as graphs. This example involves patents, which is assumed an unit of innovation, and also it transforms technology to science. We are trying to build techniques that would save resources to file these patents, also help in better decision makings where monetary loss is involved, as well as we are trying to understand how innovation happens. So if you have read this book, Outlier, you might have known that success not only depends on someone's individual capacity, but also depends on some other settings. We also found very similar results with innovation, that innovation doesn't happen depending on a particular technology's merit, but it also depends on which other similar technologies are growing together. So with that, thank you all. And if you are interested, please contact us and apply at UIC. We also wish you all the best for your applications and for your PhD.
Cool. Our next speaker is either Mark Richanek, who's not here, or Stavros Sintas. So Stavros, you're next. Go ahead and share your screen whenever you're ready.
Yeah, hello. Okay, can you see it?
Yep.
Yeah, okay. Yeah, hello everyone. I'm Stavros Sintos. I'm a new assistant professor at UIC, and today I will briefly talk about my research, which is on efficient indexes for data queries, combining geometry with query processing. So let me start with geometry. As Plato said, geometry existed before creation. we as people and our human minds are very good on understanding and analyzing geometry because everything around us has a geometric shape. But what about geometry in data? What is the role of geometry in data? Interestingly, there are many applications such as visualization or geospatial analytics or molecular biology, where applications are inherently accompanied with geometry. So geometric algorithms are used in these fields in order to derive very efficient and practical algorithms. In addition, in databases, many times we want to solve data queries, and we want to construct, and in these cases, we want to construct some data structures. And most of them, like KD trees or R trees, are some tree-based data structures where the goal is to partition the space. So in this case, we assume that data lie in a geometric space, and we want to find the best partition so that we accelerate the data queries later. So it is generally known how to use geometry in databases. However, in modern data science, there are a few new challenges that we need to consider. First, we say that we live in the era of big data. So sometimes we have data queries that need to run on a really large amount of data that we cannot even store in memory or in disk. But even if we do not have big data, even if we can actually store all our data in disk, the problem is that with the dataset becoming more complex, data queries are also becoming complex. So we want to make sure that we satisfy some constraints on fairness or diversity that makes like the problem much more challenging, and we need new ideas in order to handle these new complex but useful at the same time constraints. Now, my research exploits generally how to use geometry and generally optimization to build efficient and practical indexes for various complex data queries over large datasets. My research has applications in a few different domains, such as interactive analytics, search engines, online stores, data compression, and automatic fact-checking. And I'm going to talk about two of them here. So the first one is on interactive analytics. So here we assume that we have a really large data set that we cannot even store in our computer. So instead, like the goal is to be able to construct a data structure based on only on a subset of data, so that we are able to answer some aggregation queries. For example, what is the sum or the count among some items that satisfy some linear constraints. So this area is called approximate query processing, and we combine geometric partition along with stratified sampling, and we are able to answer aggregation queries, and we return unbiased estimators with provable guarantees on the confidence intervals. And in addition to that, we actually implement this data structure. We build a system on Apache Kafka, and we compare with other state-of-the-art data structures on approximate query processing, and we are able to outperform them in many cases. Second, I've worked a lot on search, on different applications on search engines. So sometimes, like in search engines, imagine we go to an online store and we are interested in buying a laptop. So we have some preferences. For example, I'm interested in laptops with RAM memory at least 5 GB. So then we want a system so that the system can show or advertise to the user a few items so that the user might find one to buy. Now, of course, like a good idea is to return items with to show to the user items with high rating. However, we want these items to be different. We do not want to return many items that are very close to each other. So here we actually construct the fastest near linear space data structures, so that given some linear constraints represented as rectangles in our geometric space, we want to return items that are good enough, meaning that they have high relevance to the query, but at the same time, they are different, they are diverse. And we are able to return these kind of items extremely fast in sublinear time, as we say. So generally, I work in the intersection of computational geometry and databases. More specifically, I like using concepts and notions and techniques from computational geometry, combine it with some database theory, and then propose efficient algorithms and data structures with theoretical guarantees. But at the same time, I'm interested in implementing these data structures and compare with other state-of-the-arts on applications in databases. And with that, I conclude. Thank you very much. And if you are interested, please send me an email. My first name at uic.edu. Thank you very much.
Thank you, Stavro. Elena, you're next.
Oh, I forgot to unmute myself. Can you see my slides?
Yeah.
Wonderful. Hi, everyone. I'm Elena Zheleva, and I'm an assistant professor in computer science. And I direct the EDGES lab, which is data science and relational learning lab. My main research areas are machine learning, causal inference, and graph mining. And I use a combination of those in order to find answers to interesting problems from different application areas, such as social media and networks, healthcare, e-commerce, and privacy. One thing that unites my research is the type of data I'm interested in. It's data where there are interactions between individuals, diseases, units, and so on. So some examples that I'm giving here on the right-hand side are, for example, users interact on social networks, ads compete for the same attention when they're shown either online or in this case at Times Square in New York, and also the vaccination status of one individual can impact the disease status of other individuals. Students also interact in classrooms, and their educational outcomes can be connected to each other. And even in agriculture, things like using certain pesticides in some plots can impact the crops in neighboring plots. So here are some questions that my research lab has looked at over time, and so we're interested in this type of questions, specifically to social media. Can social media interactions make users vaccine hesitant, and why? Can misinformation campaigns on social media influence elections? What messages in online support groups cause people to feel more empathy? What social interventions can facilitate the viral spread of a message or a product? And many more. And here I have highlighted certain words in these questions. Why, make, influence, cause, interventions. These are all keywords that actually point to causal inference. We're interested in causal insights from data. And overall, I'm very interested in identifying and resolving barriers to causal inference from relational data where people interact or diseases interact for real world applications. And what I'm showing here is a simple pipeline of my research, where I work on various aspects of this pipeline. So we start with some data, and then when we start with some data, we typically don't know what is the causal mechanism that actually created the data, but it's actually necessary for us to be able to answer causal questions. So the first thing we need to do is learn what the potential causal mechanism was. Once we do that, then we can do estimation of various causal effects that we may be interested in, like based on the example questions I show above. And moreover, we may be interested in how these effects are different across different populations, something known as heterogeneous treatment effects. Another area of research that my lab is interested in is unbiased recommender systems. So recommender systems are all around us. They guide recommendations for what to read, who to date, and so on. And these recommender systems rely on historical data, which is often biased. So they would take some data where something was shown to a user, maybe a user clicked on something or replied to something from these items or purchased one of these items. And then this click data is passed on to an algorithm that learns from it. But this data actually has many different biases, such as position bias. You tend to read from top to bottom. Therefore, you're more likely to click on items that are higher up. Sometimes you don't even see items that are closer to the bottom. And when we have such biased data, causal inference can actually help with answering things like, would the person have clicked on this item if the system would have shown it to them? And that's where causal inference comes in. And so the overarching research goal here is to improve learning to rank systems by addressing inherent data biases through causal inference. And if you're interested in learning more about our research and our publications, please visit the website, which I have posted at the bottom. Thank you.
Thank you, Lala. Barbara, you're next.
Please give me just a second to stop sharing. Yes.
Okay, let me start again. Okay, do you see my presentation fine? Hello?
I can see your presenter view, not the
Okay,
slideshow.
better?
Oh, same thing. You might need to quit and then restart. But you know, this will work as well if you just want to do it this way.
I do swap displays after I start.
That might be why. But you know,
Is this okay? Or still is the,
I can still see all your slides in a panel.
okay, let me, now?
This is good.
Okay. All right. Hi, everybody. My name is Barbara De Eugenio. I'm the director of the Natural Language Processing Lab, and I'm also the director of graduate studies. I always like to start with showing some pictures of my PhD students who have graduated in the past, because I think it's a good way of seeing the accomplishment of many people who have helped me in this research. So what I do is natural language processing, and I call it natural language processing with a purpose, because I am interested in application that ultimately might have a positive effect on society, and that are highly interdisciplinary. I'm very keen on studying how people interact with AI artifacts, in particular using language, and I will illustrate some of those in this talk. If my slides let me, okay, there. All right, so I work on conversational agents. Now, of course, conversational agents are in all our lives, Siri, Alexa, and whatever you have. But we are interested, as I said, in application that can make a difference in people's lives. So, for example, I collaborate with people in the electronic visualization lab, and in using natural language dialogue for visualization with the idea that people don't need to know how to visualize complex data. They can just ask the system for charts of the data they have to they are interested in, and the system will help them get insight into this data. Another application area that I worked in for a long time is natural language processing for educational technology. technology, in which, in collaboration with the cognitive scientists, we studied tutoring strategies that human tutors use to teach actually introductory computer science, and use these strategies in an intelligent tutoring system that we experimented with more than 500 students in different classrooms and different campuses. Another kind of natural language based interface is now in healthcare, where I have several projects, a virtual health coaching system that uses SMS. We want to support human health coaches in helping patients adopt and fulfill SMART goals that are specific, measurable, and so on. We collected 2 data sets of these exchanges between a health coach and 28 different patients. And you can see here in this snippet that the coach is helping the patients adopt a SMART goal and predict what barriers they might encounter. So for example, here is a patient who wants to be more active. The coach asks, what do you think will make it difficult? Not being able to walk during my lunch hours because it's busy at work. And then the coach might say, okay, so if you cannot work during your lunch hour, can you walk when work finishes? We have a prototype that recognizes the agreed upon goal and generates potential messages that the human coach can choose from. Another kind of project is multimodal conversation for assistive robots. Here, again, in healthcare, we are looking into helping older people age in place, and we collected data in which an assistant helped the elder person perform activities of daily living, meaning, like setting the table, prepare dinner. And so these are multimodal conversation where people, there is language, but there is vision, and there is also haptics, force exchanges. And then we use these dialogues that we model in various ways to develop robotic interfaces that can do that sort of things. Here we see the human pointing to a box where the robot needs to find some object. And if you notice the open drawer, that's a drawer that the robot has opened in the previous portion of the dialogue. I'm almost at the end. Just want to talk about another project also in healthcare about information presentation and summarizations, where we want to provide patients with a clear, concise, lay language, personalized hospitalization account. This happens when they leave the hospital after they have been hospitalized. This account will integrates, not will, because we have done it, doctors and nurses documentation and be informed by the patient's socio-cultural perspective. This includes summarization, simplification, because the doctor's language is always very complex and full of jargon, and personalization, trying to personalize the summary so that it helps the patient follow up with visits and with medication. And I think I am about at the end of my time. I will stop here. I should also mention that I'm the director of the Natural Language Processing Lab. Another professor, Natalie Pardee, is the co-director. She also has a vast number of projects. And so if you're interested in NLP, please get in touch. Thank you very much.
Ben, you're next.
Liz, it's my turn, right?
Yes, you're next. Go
Okay.
ahead.
Can you see my screen in the presentation mode? Okay. Thank you for attending this session. My name is Bing Liu, and professor in this computer science department. My current interest, I had many interests in the past, but my current interest is the lifelong or continual machine learning. Basically, I'm interested in machine learning and also natural language processing, but currently I'm more interested in machine learning. And the first topic is lifelong learning, and the second one is autonomous AI, and how can we make the system to learn to behave sort of by itself, okay, become autonomous instead of being trained and or monitored, trained, retrained with the initiation from the human engineers. So traditional machine learning basically follow this kind of a paradigm where you have a particular task and then you get a data set, and then you go for machine learning algorithm, run the machine learning algorithm, then you produce a model, and the model basically be applied to the application. And this is what we call isolated single task learning. Okay, so there are many weaknesses. Okay, obviously this is not what we humans do. Okay, the first weakness is a closed world assumption, which basically means whatever you learn is whatever you see in the future. So whatever you see in the future must have been seen in the past. So that's not really true in real life, because in real life we have an open world, and there's a lot of unknowns and a lot of things which is unexpected. So how do you deal with that kind of situation is a major difficulty. And the second part is traditional machine learning does not do continuous learning. So as we humans do, we basically every day we learn and they keep accumulating knowledge. And so currently the machine learning still cannot do that. And current machine learning still do basically learn each task in isolation. And there's no accumulation, there's no knowledge transfer in a large scale. Another thing is, as you can see from this diagram, the machine learning is basically when you go to the application, that's it. And there's no learning after deployment. So we want to make this model to improve itself after the model has been deployed in the application. So this is very useful. For example, we have chatbots, and then when you have a chatbot, you need to talk to people. And obviously people will, can say anything to the chatbot. And so there'll be many situations that the chatbot does not understand what people is saying. And so then we want this chatbot to learn sort of during conversation. And we want the chatbot to learn new knowledge. And also we want to get the chatbot to learn new language expressions it doesn't understand. Okay, so how do you do that? Obviously, you have to interact with people and with the user, which is basically whatever that person is conversing with you. I mean, we humans learn a lot of stuff in our daily conversation, and we don't want this to be sort of like traditional way you retrain the system all the time with on the initiation of human engineers. Okay, we want the system to do it itself, can do everything itself. So here is another example of self-driving cars. Right? What is the difficulty of self-driving cars? Because it's really tough to cover, all kind of corner cases when you come to teach this self-driving car to drive. And I work on this thing for 1 year, and I find it really tough. I'm sure everybody knows that no safe self-driving car yet. Okay, because the real world is really full of unknowns, and it's really tough for a system which is trained by labeled data and to be able to behave sort of in many kind of unexpected situations. So in those kind of situations, obviously the system had to interact, also adapt the situation. Interact with the system, with the user, and with the environment, and then try to adapt. So let's give you sort of my personal experience and when I consulted for a company on self-driving. Right? And once we took a car for a road test, and then the car comes to a T-junction and it suddenly stopped and refused to move. Okay, because obviously there's some dangers in front. So we look front and look at the back, look at the left, and look at the right. There's nothing on the road because obviously this is the road test. We didn't really go to the busy street. I go to somewhere in the suburb, and there's not much. There's not much traffic at that time. There's nothing. Okay, so the car just refused to move, and we have no idea what's going on. And then our manual driver, our human driver, had to take over. I drove the car back to the lab. Then we go, to figure out what's happening. Okay, and then we debug the system. We find, and one of the sensors detect a small pebble on the road. And then the human eyes, we don't really notice. We don't really notice that thing. But then this guy detects something and just don't know what to do. So if this is a situation, if the system can interact with us, okay, with the driver or with whatever the passenger inside the car, if the car can say something, right? For example, can say, I detect an unknown object here, and what should I do? And as the passenger, and our human driver just can reply, it's safe, just go ahead, right? And in this case, and then the car basically can drive ahead and basically go back to the lab. If this can be done, and that'll be really great. And because this basically I'll be learning on the fly. On the fly, and the next time when this kind of situation occurs again, and then there will be no problem. There will be no problem. So this basically is a continual learning process, and also an autonomous. It's an autonomous system. Okay, it becomes an autonomous system. So in terms of research, essentially what it means is that we are learning a sequence of tasks. You can see on the top, we have task 1, task 2, task n. And what is the current task? The current task is Tn+1. And obviously we need training data. And the training data goes to the learning algorithm. And the learning algorithm is able to leverage the knowledge we learned in the past in order to learn better to produce a model. And then this model goes to application. So during application, while the system performs its intended tasks, and is also detecting new tasks. So for example, just now the system detect a small pebble, a stone on the road. And then it basically should automatically create a new task. So that's the stuff the system needs to learn. And then it also has to collect data in order to learn. So then you can ask them, but for example, in that sentence, you just ask the human being, what's this stuff is, and whether it's safe to drive ahead. So then you get that as a piece of supervisory information, right? And then you can take a lot of pictures of that thing, and then essentially you can learn that stuff, and then that's a small pebble. And then you also know it's safe. The next time you will not have a problem. So you can see we get a closed loop. So the system become autonomous, which we call it open world continuous learning, or we call it open sort of AI autonomy. Yeah. That's pretty much what I want to say, but I can give you another example if you have time. So this is a greeting bot in the hotel. Okay, in the greeting bot in the hotel. And when this bot sees existing guests, so for example, you have robots roaming around in the hotel lobby, and basically try to greet the guests. Yeah, for example, this bot sees some person comes out, and they can say, "Hello, John, how are you today?" Because this bot sort of recognize this person, know this person. And what happens if the person has not been seen before? This guest is new, and so this robot has to sort of recognize this person is new. So this is essentially a novelty detection problem. Okay? You want to detect something which is novel happening in your environment. So then you have to react. How do you react? How do you adapt this kind of situation? Because you have never seen this person before. So in this case, of course, you can say, "Welcome to a hotel, and what's your name, sir?" Okay. Then the guest may say, "David." So you can see you get a class label, right? You get the training data and class label. Because the training data, you can just take picture of this person, and then you continue learn this person. Okay, incrementally learn to recognize this person, and after that, next time when you see David again, then you say, "Okay, hello, David, and how are you today?" So you can see this process again. It was trying to stress this is an autonomous process without engineer involved. There was an engineer involved. So that's pretty much what my objective is. But I'm not doing everything here. I'm basically doing out of distribution detection is try to recognize this person is new, and also learn sort of continuously, learning continuously to recognize this person. And so if you're interested in this particular area, and you can contact me, and I also can see my research page, which is about lifelong learning. You can get lots of information from there. And if you're interested, yeah, just email me. That's it. Thank you.
Thank you, Bing. Nikita, you're next.
Yeah. Okay, can you see my screen?
Yes.
Okay, great. So hi, everyone. I am Nikita Soni, and I'm a faculty member here at UIC CS department. And my main research focus is in human-computer interaction. And I'm really excited to talk to you about my research today. So as a part of HCI, or it's called human-computer interaction, I largely focus on natural user interfaces for education and creativity. So natural user interfaces are basically interfaces that allow users to interact with a range of human senses, such as touch, speech, or whole body input. And they have been used in multiple application areas, including education and creativity. So think about how many times while you use touchscreens or speech interfaces, you found yourself figuring out how to operate the interface rather than focusing on the task that you're doing, maybe learning or doing something else. So in my work, I try to build natural user interfaces that leverage users' natural interaction behaviors and that do not interfere in their learning and creative goals. And I largely pursue this research in 3 phases and majorly in 3 application areas. So firstly, my lab works closely with end users as stakeholders of the technology, and these end users are from different age groups, ranging from children, they are undergrad students, they are family groups, and we learn about their needs, we learn about their capabilities, and also study closely how they currently use technologies to meet their goals. And we do this through conducting user studies such as focus groups, interviews with people, we talk with them, we involve them in design process, and we have done similar studies in multiple contexts, including in research labs, in classroom settings, as well as in museum learning or public learning spaces. So secondly, we leverage what we learn from users to draw design insights, to build new user interfaces, and also to develop recommendations for designing natural user interaction recognition algorithms. And again, we do this by iteratively prototyping software applications based on what users are doing and where we see opportunities for designing. And we also develop data sets for users' natural interaction behaviors that could then be used to test and train existing or new interaction recognition algorithms. And finally, my lab is really interested in studying how can we translate whatever research we do or research-based guidelines we come up with for practitioners, because usually practitioners are the ones who would be implementing these guidelines into developing technologies that would be used at scale. So for example, one of the work I'm doing, one of the stakeholder I'm working with to develop translation materials is with children's app developers who often develop commercial applications for iOS apps, iOS platforms or Android platforms. And in this, we have developed translation materials such as toolkits, frameworks, also some design patterns, so that they can easily adopt whatever research findings we have without reading through research papers and making the process time-consuming for them to adopt. So through this process, as I mentioned, I'm interested in exploring 3 application areas. The first is around understanding how to design educational tools to support learning about Earth system science and climate change processes. And we have done this both in Earth science classrooms and public learning spaces such as museums. And some of the applications which I've designed have been used by hundreds of family groups in museums and is being used in classrooms this semester. So we are pretty excited about this project. The second application area is in the context of privacy education and natural user interfaces. So through this, we are looking into how can we use natural user interaction technology to teach families about digital privacy, to teach them how these NUIs work. For example, how does your Google Home work? How does the information flow or data flow happens when you talk to this NUI technology or smart home devices, and educate families about that. And the third application area looks into using natural user interfaces for creativity and graphic manipulation. So I'm primarily looking at using touch and speech to augment graphic manipulation experiences rather than relying on heavy lengthy menus and icons. How can we augment natural interactions to make these tasks easier? So this is the general overview of my research. If this is the type of work you are interested in, please contact me. My email is here on the slide, and you can also find more information about my work on my webpage. Thank you.
Cool. Thank you, Nikita. Joe, you're next. Joe, are you ready? Okay, if Joe is not ready, then Ian, can you go next?
Sure. So hi, I'm Ian Kesh. I work at the interface of economics and computer science. So if you want to get to know me at UIC, you can take my specialized course on that. I also teach the broad AI course. And to kind of give you a flavor of the sort of things I do in my research, like what does economics have to do with computer science? Well, one area I work in a lot at the moment is cloud computing, looking at questions of how resources in cloud computing are priced and how this turns into resource allocation problems for the cloud provider. So one kind of current example I've been working on is serverless computing. And the idea here is you give a big cloud provider like Amazon or Microsoft a piece of code that you want them to run in response to an event, which might be a timer coming off or a web request coming in, and then you just pay for the amount of time they spend executing the code. But then, from your perspective, this is very simple. From their perspective on the back end, though, they have a bunch of kind of complicated resource allocation problems to solve. For example, one task they have to decide is, okay, your code has just run. Should they keep it in memory where it's going to be fast to run it again? Or should they kind of page it out to disk and reclaim those resources? And those resources are costly. They could be using them to cache other people's functions. They could be using them to run other cloud services on. There's a real cost for keeping it in memory. And so they kind of have to make a trade-off for this. And what we did in this work is we wrote down a simple model for how you trade off between those two costs. And then we can find out, sort of derive the form of optimal policies in various situations. So if you've seen simple queuing models like with some processes, it turns out that the optimal solution there is to either evict the user's process immediately or keep it in the cache forever, depending on the intensity of arrivals of the process. We've studied more complicated and interesting processes like Hawk's processes, which are kind of where one event triggers other events. So you could think of this as like a web server where somebody shows up and then they're browsing around, causing more events. These are also used to model things like earthquakes and aftershocks. So they're kind of a fun stochastic process. And we proved some approximation results about the quality of various policies. And we did some testing on a data set that Azure has released on this. So that's kind of gives you a flavor of the style of my research, where I tend to have a theoretical focus. We're kind of proving theorems, but also doing some testing it out in domains. I kind of do this in lots of different domains. So I've worked on ride sharing, understanding kind of the decisions that Uber and Lyft make when they're setting prices and trying to figure out which cars to match to users. Kind of a more abstract domain is information elicitation, which sounds very dry, but if you care at all about the design of auctions to sell, say, advertising on the internet, or the way you choose a loss function in machine learning, or the way banks are regulated to ensure that they don't take on too much risk and blow up the economy, or the way that you might make the conference review process in computer science better. This is kind of a fundamental underpinning of all of these areas. I work on reinforcement learning in multi-agent settings, kind of building on learning in game theory. And also I do some work on writing some of these ideas of fairness, which run through economics, and thinking about them in the context of fairness in AI work. So that's it.
Cool. Wei, why don't you go next?
Sure, I will share my screen.
Great, thank you.
Hi everyone, I'm Wei Tang. I'm an assistant professor in the Department of Computer Science. I joined UIC in 2019 after obtaining my PhD degree from Northwestern University. And my research area include computer vision, pattern recognition, and deep learning. And so now I will briefly introduce a few projects we have worked on in the past few years. 3D human pose estimation means to estimate the 3D posture of a person from a single image or video. And this is very useful in a lot of applications such as robotics, human-computer interaction, and special effects for movies and animation. Our idea is to modeling the diverse and high-order relationships between body joints via a novel graph network. And this new method is very effective and it can reduce the error by 10% without increasing the complexity. This is a very short demo of our system. And we can see that most of the time it works well. Of course, it is not very perfect because this is a very difficult problem. Another project we have worked on is human action detection. So given a video, we want to recognize the action of interest in the video and also locate their starting and ending times in the video. This is very useful for robotics, video editing, and retrieval, and security camera. So our idea is to modeling the local and the global context of the actions in the video. The local context means the frames within an action. And this is very important for accurate localization of the video in the localization of the action in the video. And the global context means the information in the whole video. And this is very useful for action recognition, especially when there is some ambiguity in the category of the action. Our approach achieves the state of the art, and this is a demo. When there is an action, it will indicate the category of the action. When there is no action, it will say no. And another project we have worked on is the semantic segmentation, and this is a very traditional task in computer vision. And it means to assign a class label to every pixel in an image so that we can do a segmentation of the image. And this is very useful in autonomous driving, medical image analysis, and image editing. So our idea is to model different levels of visual dependency of the objects in the image. So the intro class dependency means the relations between different parts in a single object. For example, a bicycle consists of a pedal, the wheel, and the frame. And the interclass dependency means to model that some object categories occur together more frequently than the others or by chance. And the global dependency means that the type of the global scene will provide a very strong prior on what kind of object categories will be in the scene. For example, it is unlikely that the bed will be occurring in the outdoor scene. And our approach is very effective, and we show that the 3 levels of visual dependency are complementary, and they can greatly improve the performance of semantic segmentation. And we have also worked on some other projects, such as no-light image enhancement, image generation, and to identify a person in a photo gallery, and also work on the zero-shot recognition. And if you want to know more information about these projects, you can visit my website, which is here. And thank you.
Cool, thank you, Wei. Fabio, you're next.
Yes. you see my screen?
Yeah.
Cool. So, hi everyone. My name is Fabio Miranda. I'm assistant professor at the department, also with the Electronic Visualization Lab. So my research is really motivated by this growing availability of data related to cities. Data creates opportunities to better understand cities and to tackle some of the problems facing them, such as housing, transportation, and pollution. However, certain problems lack data, even though we live in the era of big data. For example, if we consider urban accessibility, we need data describing sidewalks. And in a recent study, they showed that out of 178 cities in the US, only 20% had sidewalk data, and only 11% had crosswalk data. So an important aspect of my research is creating new, large and complex data sets that describe the urban environment. And given that we can now have this new urban data, how to make sense of it. For instance, in a recent project, we're deploying camera-equipped sensors at railroad crossings, recording 24/7, generating a total of 350 terabytes worth of video data. So an important question in my research is, how can we extract insights out of this data? Another important aspect is how can we empower experts in the analysis of this data. Over the years, we have been proposing visual analytics tools that enable experts to analyze multiple large and complex data, including image data, audio data, as well as weather simulation data. So my research can be framed as follows. First, creating the techniques to measure the built environment, creating new data sets. 2, the techniques to model urban phenomena. And 3, creating the visual analytics tools to inform both urban experts as well as urban communities. In my research, I focus on some very concrete urban problems, including accessibility, pollution, sunlight access, and the impact of climate change on cities. And one specific aspect of cities that fascinates me is the fact that cities are becoming increasingly vertical, either through usual forces that lead to the creation of taller and taller buildings, or through economic pressures that make people build on top of hills and mountains. So in order to tackle the problems that are inherent to the 3D urban space, I propose new interaction techniques for the labeling of 3D point cloud data in models that can segment parts of the city according to their material, such as segmentation of sidewalks, taking into account whether it's made of bricks, asphalt, etc., or the segmentation of building facades, taking into account whether they are made of glass, stone, etc. I also propose new modeling schemes to understand urban phenomena, such as the impact of noise or shadows on public spaces. In one of these research lines, we use the technique proposed by us to compute an interactive map of shadows for an entire city of New York. And we computed the current shadow situation at 3 different days of the year in each season of the year. And we extended this work to go beyond 100 cities in the world, enabling us to assess the sunlight access situation at a global scale and compare cities regarding the impact of shadow on public space across continents. I'm also interested in the design of new visualization metaphors and navigation schemes that allow experts to analyze data that's inherent to the geometry of buildings, while accounting for problems such as occlusion. In a recent research, we ran a user study to measure how different users interact with 3D urban data, and the results led to a series of design recommendations on how to best build visual analytics tools that leverage that sort of data. So if you are interested in any of this, please feel free to reach out. Thank you.
Thank you, Fabio. And Joe, do you want to give it another try?
Yeah, let's try. Sorry, everyone, my connection freaked out as soon as I tried before. But let's see. Okay, so my lab is the Learning Interest and Technology Lab. And the kind of research that we do is based on human-robot interactions. I sort of combine elements from learning sciences research with social robotics and computer science work, and really think about long-term interactions with robots that can help people learn better, to develop interest in what they're learning, and how to design social robots to help facilitate that. So Nikita kind of describes some similar sort of methods to what she does, I do as well, in a human-robot interaction model. One of the important steps that really guides a lot of the work is to really examine how people work and understanding how they interact, particularly in social and learning scenarios, and use that information to help us develop interaction models for the robot to work with kids. And then to implement that onto a learning technology, typically for my work into a robot. And another key portion for what I do that's a little bit unique is that I always really focus on integrating this work into real world activities. So real classrooms, real homes, libraries, community centers, not just in the lab. But we do assess the outcomes of how these things are working in all those settings and in some lab studies as well, just to kind of hone in on some of those details. But that process is something that I apply in kind of two main areas. One is using social robots as a platform for students to learn computing and computer science. The sort of social components to designing a robot that can work with people, for people, help communities, is really compelling to a lot of students. And the physical artifact of a robot is really beneficial to helping them see the outputs of their programming work come to life in the real world. So we run a summer camp. We're also working on some after-school programming as well. The other side is to design social robots as learning companions, where we think about all the elements that go into these interactions. The image that's here is some of the work I've done on understanding how robot gesture use can impact the way that people learn and the way that people interact with robots in these learning environments. So when robots are more illustrative of what it is they're trying to reason about, in this case in a geometry scenario, the people respond in kind. They use more gestures and they use a more rich language in describing what they're doing. So in understanding all of those, my main sort of thread for project right now is a recently NSF funded Pathwise project, where we're actually developing a tool for teachers to create their own robot interactions in their classrooms. So the idea is that the teacher can kind of design these interactions and then kids can do those at home. We're also exploring how they can do those in after school or like library scenarios. So our current prototype in that area really allows teachers to kind of bring in whatever sort of comments or things that they would want to say to kids while they are reading a science related article. They can create their own. They can pull in some examples that we have. We're also working on an automated tool so that we can automatically generate new comments based on the text that's on the screen. And then they can sort of preview what it would be like for the robot to play that. And that all gets stored on a database where a kid then can log in on their own home screen with a robot. And we pull all the teacher comments and information from our database, push that to the robot interacting with the kid in this scenario. And then kids can have not only this really robust social learning experience, but one that's been very tailored to what they need for their classroom by their teacher. So this is a sort of ongoing project that just got a little boost from some new funding. And we're definitely continuing along some of these other lines. So if you're interested in any of this sort of work, happy to talk more. You can check out some of it at our website at the bottom there, or feel free to send me an email. I'd love to talk about it. Thanks very much.
Cool. Thank you, Joe, and thank you, everyone. I don't see any open questions, but I think we all have provided our contact information. So if anybody has questions, they can reach out via email. And with this,
Liz, there is one raised hand.
Okay. Ayushi?
Good morning, professors.
Hi.
My name is Ayushi Gaur, and I am doing an MS in Business Analytics here at UIC. I was also doing a PhD in deep learning, back in India in one of the leading institutes, but I left after 2.5 years, and I'm here trying again. Should I go for a MS in thesis, or should I go for a PhD? What would you suggest? I also wish to work on social robots for learning, or for human pose estimation, human interaction, human-computer interaction, deep learning. These are my areas that I've worked on in the past few years, and I want to give a second chance to my research. My question is that I'd wish to know if I should go for an MS in MS with a thesis, or should I go for a PhD?
Anybody would like to take a stab at that? It's a complicated answer, I think.
I mean, if you're on campus and you're interested in HCI and HRI work, send me an email. We can set up a time to meet and talk about it. But Liz is right. It sort of depends on more details of your background. Generally, though, if you are very interested in academic research, the PhD is probably the way to go. The thesis option for your master's is going to be a good start. But if you're pretty certain that's what you want to do, PhD is probably the right line. And if your qualifications are in place and if you can get admitted for a PhD program, that's what I would recommend. So yeah, reach out, let me know, and we can try to sit down and talk about it at some point too.
Thank you, Professor. I'd mail you about the same.
That's the graduate admissions website on the computer science website. There's a tab for what we consider to be core courses in computer science that our graduate students have typically completed as part of their undergrad. It doesn't mean that if you have not taken those courses, you will not be admitted into the graduate program. It means that typically we expect graduate students with a degree in a related field to take those courses during their first couple of years of study.
Thanks for letting me know, Liz.
All right. Any other questions? Ahmad, go ahead. Ahmad, you can either speak or you can type your question in the Q&A. Yeah, we can hear you.
Yes, I have completed my master's degree and my thesis was about natural language processing, especially in Arabic language. Do I have a chance to have my PhD natural language processing in your university?
Yes, of course, you can apply. As I said, we have a large group doing natural language processing, either directly or indirectly, meaning I presented my own research, but as I said, Professor Natalie Pardee is the co-director. And then, as you heard, Professor Bing Liu is also interested in natural language processing, and many other colleagues as well from a variety of point of view. It could be more from human-computer interaction, or one of our newest colleagues, Lu Cheng, who works on bias and fairness in AI, also has several applications in NLP. Professor Zeleva also, some of the data. In fact, Professor Zeleva and I have collaborated as well. So there is lots of research in NLP going on. So if you apply, then, we can see what the best fit for you might be with all the people who are, as I said, directly or indirectly working on natural language processing.
Thank you very much.
And I will add that we always like when people do have some background in NLP, which sounds like you have, like having done your work, your undergraduate or master's in NLP already.
Thank you very much. Thank you.
Good. Any other questions? There was a question about the requirements for applying to the program, and we covered them earlier in this presentation. They're also on the departmental website, and I posted that in response to the question. All right. If this is all, then thank you, everybody. This recording will be posted on the departmental website under the graduate admissions page. And other than that, thank you all for attending.